So hello everyone, this is lecture 15 for the classical physics. The last lecture we were discussing about the escape velocity and we completed that topic. So today we will see about the orbital velocity and some questions based on these topics. So what is orbital velocity? So any satellite or natural satellite, or it can be anything which is moving around our earth and rotating or periodically, so we call that orbiting to our earth. Okay, so we need to find the velocity of that object, or at what velocity we can throw an object from our earth so that it will start rotating around the earth. So that is called the orbital velocity. So see, to rotate anything around the earth we need a centripetal force. So that centripetal force is given by the earth's gravity. So at any point at height h, okay, we call this distance from here to here is r, this height is h, this radius is r. Okay, so the force on this mass will be gmm over r square, the magnitude, and this will act as the centripetal force. That's why we equate it with the mv square over r. From here we can find this v orbital. So from here this velocity will be orbital velocity, so vo will be gm over r. So this will be our orbital velocity. Now you can write it in the form of radius of earth. So it will, r is nothing but r plus h, so vo equal to under root gm over r plus h. Here you know small g is gm over r square, so gm can be gr square, so r square will give you r outside, so you will get this form. And if h is very small as compared to r, then you will get what? This r square will came inside and it will cancel out, so you will get rg in the under root. So at the close to the surface h is less than r, so v o is nothing but under root rg. So this is your orbital velocity. And remember what was escape? It was under root 2 rg. So v escape divided by under root 2 will give you orbital velocity. So this is the relation between orbital and the escape. V escape divided by root 2 will give you orbital velocity. So if you find this value, it will be 1.414 vo, means v escape will be under root 2 v naught. So this is this. So v escape is 40% greater than orbital, or we will say that 141% of orbital velocity. Okay, so from this number you can find this percentage. Now see, orbital velocity is always less than escape velocity, and it is nearly 40% more than this. So we already find it this. Now let's see how speed determines the orbit of the satellite around the earth. So if velocity is less than this orbital velocity, then what happened? If we launch something from the earth and the velocity is less than this orbital velocity, v is less than vo, then we will have a parabolic trajectory. Means object is here and velocity is less than vo, then it will go like this parabolic path. The normal path we see, it will go to that path and will hit the earth. What happened when v will become v orbital? So if here velocity is v orbital, then it will go around this earth in the circular orbit. Okay, so orbit will be circular. Now v is greater than vo but less than ve. So what happened? We will have a elliptical orbit. So see here, it is more clear here. Means first it was parabolic, then when it becomes v equal to v naught, it will be circular. Then now v is greater than vo and less than ve, so it will go elliptical. And when v is increased from the escape velocity, it will go to the infinity, hyperbolic. Okay, so we already defined these things with the help of eccentricity. Now we are describing it with the help of velocity of the object, that what kind of orbit we will get. So remember these values, these are very important result, helpful for solving the questions. Now you can also find the time period. In the circular orbit, the whole distance covered will be 2 pi r and speed will be v naught, so time period will be 2 pi r over vo. So vo is, we already find it this, it is under root gm over r here. So just substitute it here and you will get time period as this. Okay. Now take this r inside, so you will get 2 pi r cube over gm. Now you can see this will give you a relation something t square equal to r cube, because this 2 pi will came this side and under root will give you a square, so t square is proportional to r cube. From the Kepler's law we know this thing. Okay, so for the elliptical orbit, what will change? In place of r plus h, we will just write a, and the time period will be same. And this a is nothing but semi-major axis. So this is ellipse, and if there is this its foci, then this distance is called from the center. The half of this distance is called the semi-major axis a. So this will be your time period for the elliptical orbit. Remember this formula. And for ellipse, we know what is the energy. Total energy is minus k by 2a. We already proved this. Okay, and here k is nothing but gmm. Okay, so this is your total energy. So these will be very helpful for solving the questions when there is some things and you know the total energy, so you can solve the problems very easily because of the conservation of low energy. That law very much helpful in solving questions. We mostly use that. Let's see the total energy for circular orbit. So it is kinetic energy plus potential energy. So kinetic energy is half mv0 square. This is for the orbital, the our satellite, energy of satellite we are finding. So half mvo square, and potential energy is minus gmm over r. So we already know orbital velocity under root gm over r, so we get this. From here, total energy will be minus gmm over 2r. So this is nothing but, if you see, this is your kinetic energy. So total energy is nothing but minus of kinetic energy. So remember this expression. For h is very less than r, total energy is minus gmm over 2r, because this r is nothing but r plus h, capital R plus h. So for small h, this will be simply radius r. So this will be your total energy. So remember these formulas. Let's see some questions based on them. Acceleration due to gravity on the Earth surface of gravity on the surface of Earth is approximately 2.6 times that on Mars surface. Given that the radius of Mars is about 1/2 the radius of Earth, the ratio of escape velocity on Earth to the Mars is approximately. So we know for the escape velocity it is under root 2rg, so 2 will cancel out, and this will be your formula for GERE. So you have this ratio also and this also. Just substitute the value and get the answer. This is very easy. Let's see another question. A satellite of mass m orbits around Earth in an elliptical trajectory of semi-major axis A at a radial distance r equal to r0 measured from the center of the Earth. The kinetic energy is equal to half total energy. Find r0 by A. So it is given that a satellite is moving in an elliptical orbit around the Earth at particular point when this radial distance is r0. We find that the kinetic energy at this point is half of total energy. So what will be the ratio of r0 divided by A? This distance is A. So we need to find this ratio. So we'll use the conservation of energy law. Total energy at this point will be equal to what is the energy of this ellipse? I already told you. Energy of ellipse is just minus gmm over 2a. So we will find the energy at this point. We'll equate that to this. So at this point, the distance is r0, so potential energy will be minus gmm over r0. So this is your potential energy, and kinetic energy will be half mv square. But kinetic energy is already given. This is half of total energy. So total energy is this. So half of this will be minus gmm over 4a. So kinetic energy is given to us in the question, and this will be your kinetic energy, half of total energy. And potential energy is minus gmm over r0 at this point, and sum of these will give you the total energy minus gmm over 2a. So now this is we came to this conclusion by conservation of energy law. Now here you can find the r0 by a ratio just simply solving this. So you will get 4/3 as your answer. Let's see another question. A particle thrown with a speed v from the Earth's surface attains a maximum height h measured from the surface of the Earth. If v is half of escape velocity and radius denotes the radius of the Earth, we need to find the h by r. So this figure was given. An object was thrown from here to the upside. It will go to the height h, then speed will be 0 here, and this is r radius, and this speed is nothing but half of escape velocity. So we need to find the ratio h divided by r. So we will again use the conservation of energy law. At this point there is only potential energy, and potential energy will be h plus r. So minus gmm over r will be your potential energy. So let's first find the total energy at this point. So velocity at this point is half of escape velocity. Escape velocity is nothing but under root 2 gm over r. So this will give you, this is your velocity at this point. So kinetic energy at this point will be half m this v square. So this will give you this 1/4 gmm over r. Okay. Now at this point potential energy will be minus gmm over r. So this is total energy at this point. Now at this point the v tends to 0 and we have only potential energy, that will be minus gmm over r plus h. Now we have this ratio, and solving this we can find the ratio h by r, that will be equal to 1/3. Let's see one more question. A planet of mass m moves along an ellipse around the sun so that its maximum and minimum distance is from the sun are r and r respectively. Find angular momentum of planet relative to center of sun. So a planet is moving around the sun, its maximum distance is r from here sun and minimum is small r. At here velocity is v1, at here velocity is v2. We need to find the angular momentum of this object or the planet which is moving. So we know from the conservation of angular momentum at these 2 points m1 v1 r equal to m v2 r. This is capital R, this is small r. From here we can find the v2 in terms of v1. So now we have v2. Now we will use the conservation of energy law. At this point the kinetic energy will be half mv1 square. This is your potential energy at this point, and again same kinetic energy and potential energy at this point will be this. From here you can use this relation v2 equal to v1 r upon r, and you can find the value of v1. So you will get v1 square as this. So now you have value of v1, just substitute it here and you will get the angular momentum, that will be mv1 r. So you will get your answer. Let's see one more question. The masses and radii of earth and moon are m1 and r1, m2 and r2. So mass of earth and radius of earth is m1 r1, for moon m2 r2 respectively. Their centers are d distance apart. Minimum speed with which, so their distance are d distance apart. Minimum speed with which a particle of mass m should be projected from a point midway between the two centers so as to escape to infinity is. So here is our earth, here is our moon, and distance between these two centers is d. So at d by 2 and d by 2 this halfway a particle is there. So how much energy, or it is asked that minimum speed. So what will be the minimum speed applied to this object so that it will leave to the infinity, means it will be unbounded. So we'll use the conservation of energy law. When it was here, what was its total energy? So let's say it is thrown with the speed ve. Okay, so half mve square minus the potential energy at this point due to the earth will be minus gm1 m divided by d by 2, for moon minus gm2 m divided by d by 2. Now at this point this will be your total energy. At infinity, let's it's just reaching infinity, so its velocity at infinity will be 0 and potential energy will be 0 at infinity by the reference. So this will be 0 plus 0. Now from here you can find the ve. So it will be equal to half mve square equal to, this will go this side and this sum will be like this. So ve equal to under root 4g m1 plus m2 divided by d. So this will be your answer. So it's like you need to apply that much kinetic energy which will just make this potential energy 0. Means total potential energy at this point is negative. So you need to make that 0. So this kinetic energy should be equal to total potential energy at this point. So that's how you can make this free from this point. Now there is one question, you should try this. In the next lecture I will give you the solution, because this is for your practice. A particle of mass m is projected in transverse direction at height h above a point A on the earth's surface. What should be v so that particle will graze along earth's surface tangentially at a diametrically opposite point B? So what is saying, this figure was given the question. So a particle is projected from here such that it will go along this path and projectile path, and it will graze to the point B. Means grazing means it is touching the ground B and going with velocity v1. Okay, means grazing means it is just touching the ground. So you need to find the velocity v so that at B point it will graze to the ground. Okay, so mass and radius is given, height is given from h height. So you need to find what should be this velocity v. So answer is this: v under root 2 gm r over r plus h plus 2r. So try to solve. Use the method of conservation of momentum and conservation of angular momentum and conservation of energy. Using both of them you can get this expression. So I have given you hint. Try to solve this. Thank you everyone.